Hi, I'm Steven, VE9QLE. I've been licensed since 2016 or so. And yeah, I guess I'll just jump right into it. So this is project goals. There's a solar eclipse, a total solar eclipse coming through on New Brunswick next year. And my team and I, we essentially want to take video and images of the eclipse from above the clouds. So we've got a gimbal operated mirror to track the sun, which we call the Agile Eye. And the idea is, the payload is going to be moving a lot. So we sort of use software to keep this mirror pointed at the sun. So we're always looking at the sun. And then we have additional cameras which are capturing images and video from sort of other vantage points. And then we are taking that and we're streaming it to the ground in real time. There's a lot of balloon launches that happen during eclipses, but there haven't really been any that track the sun, and there haven't really been any that transmit the data down to the ground in real time. And we're transmitting that video over the 70 centimeter band. And then once it's at the ground, we are restreaming it onto YouTube and to other nearby cities. So that's sort of the overall goal of the project. So Saturday's launch, this was primarily just to test that a 70 centimeter downlink. Since this is sort of one of the differentiating factors of our project, it's sort of critical that we get that correct. So it pretty much went as flawlessly as we could have hoped for in terms of the communication system. We launched at 9 a.m., achieved a maximum height of 27 kilometers and a maximum distance of over 50 kilometers, and the system worked flawlessly the whole time, which I was really pleased to see. Yeah, so onto a bit about the payload. So our payload is quite massive for most amateur balloons. It weighs a little over 10 pounds, and realistically, it's bound to get a little bit heavier before the final launch. So there's a lot of, at least in Canada, it's fairly relaxed when you're below a certain amount of lifting gas, but we well exceeded that. So we had a ton of regulations to follow. Sort of the most important ones, I guess, from my perspective, was we had to notify the Boston Airport and Moncton Airport before launch, and they sort of had full authority to ask us to move our launch to a different time or date, or even just cancel last minute. We had a bit of trouble with that, but nothing show-stopping yet. So in terms of the electronics on the payload, we have 6 Raspberry Pis. So 4 of them are Pi Zeros and essentially just run a couple of the cameras. And there are 2 Pi 4s which handle a few miscellaneous tasks, such as data logging, video encoding, and the communications themselves. So video coding especially is super CPU intensive. Originally, we just had the 1 Pi 4 when we were just sending images to the ground, but now that we're doing video, we added a second Pi 4, which is pretty much solely just for video encoding. And also we've got 4 transmitters on board, which again is quite a few for an amateur payload, but in this case they're all necessary. So we've got an APRS transmitter, which is basically just for GPS tracking, 70 centimeters for the high-speed data, which I'll talk about in a second, and a 33 centimeter transceiver, which is essentially for sending commands to the payload, which is pretty much just for emergency purposes if we need to run some kind of command if something goes wrong. But in most normal operations, we shouldn't really be using that. And then we also have an aircraft transponder, which is for regulatory purposes. This was essentially required of us to purchase an aircraft transponder and put it on the payload. So this puts out a ton of power, about 250 watts of RF, and this interfered with a lot of stuff. It caused Pis to reboot, caused data buses to get locked up or corrupt. So the reason the payload is as big as it is we had to move that transponder away from the rest of the electronics. So in the sort of the hexagon you see, it's right at the bottom, and then the rest of the electronics are in view in the open panel. And yeah, again, that's purely just because the transponder puts out so much RF that it was just interfering with everything. So that was sort of our easy fix for that, and that basically eliminated the problem immediately. So it's good that we had an easy solution there. All right. So yeah, I'll talk about the 70 centimeter downlink. This is essentially what I've contributed to the project. Most of what I've talked about has been other people's work, but this was pretty much all my own. So yeah, the software and hardware was almost entirely written from scratch by me. So there was a bit of code reuse from a project called VE9QLE. And what they're doing a similar thing where they're doing high speed data from a high altitude balloon, but they're not doing quite as high a data rate. They're doing about 1/5 of what we can do, and they're also only doing images, no video at all. So there was some code to use there, but there's definitely a lot of stuff to rewrite from scratch. And another bit of code that we borrowed was from a utility called SSDV. That's a Sierra Sierra Delta Victor, and that it's essentially like a slow scan television, but it's digital. So you give it a JPEG, and it sort of packetizes it, and then you send the packets over the air. And the idea is if you lose some of those packets, you don't lose the entire image. You just lose a couple of pixels corresponding to whatever packet you lost. Um, and if you just sent like a JPEG over 70 centimeters and you lost part of that, uh, essentially the entire image would be useless. So there's sort of some resiliency just by doing that. Um, and yeah, we're operating very close to the Shannon limit, which, if you're not familiar, is essentially the maximum amount of sort of channel capacity that we have available. So we're basically right at the sort of theoretical limit of what we can do. We've got LDPC encoding for forward error correction, and we're using soft bit decoding on the ground. And those are all just to squeeze every last decibel we can out of the system. LDPC encoding is, I believe they use it on some space probes. The idea is you essentially have some redundant bits that, if bits are flipped, you can sort of detect and correct them instead of throwing the whole packet away. So that sort of gets us as close to the Shannon limit as we can. The theoretical range was calculated at over 250 kilometers. For Saturday's launch, we were able to test up to 50 kilometers just because that's how far the balloon happened to go. But it worked flawlessly at this distance, and the signal was very strong, very uh, good looking, I suppose. So we definitely could push that further. And we only lost contact with the payload once it dropped below the horizon at about 1 degree angle of attack for the ground station antenna. So this was actually low enough that we saw it come through the clouds on the way down, and we got an image of the ground where it was about to land, basically, and then that's when it finally cut out. So I was very pleased with that. I expected to drop out at quite a bit higher, just because 1 degree is super close to the horizon. Um, yeah, so we're using an RF4463 transceiver module, and that's sort of in the pictures. That's the metal rectangle you see. And the RF4463 is basically an SI4463, which is a transceiver chip with a 1 watt amplifier on board. So they essentially do the RF routing for you and RF design for you, and you just give it the bits you want to send, and it'll give you a 1 watt signal. So that simplifies things. We're running in at 500 kilobits per second. We could run it at up to 1 megabit per second, but we'd have to move from 2 FSK to 4 FSK. And this would complicate things a little bit on the ground side. So for now, we're just running it at 500 kilobits per second, and that's probably where we'll remain. But we do have the option to double that data rate if we really needed to. So I'll talk about the pictures a bit. On the top is the V1 board design, where we were taking data directly from the Raspberry Pi. Yeah, so these boards will sit on top of the Raspberry Pis. That's what the black header is for on the bottom. So yeah, we were originally feeding data directly from the Pi into the transceiver, and we were finding the Pi wasn't able to keep up with that. The buffer on the transmitter is pretty small, and when the Pi would interrupt us for preemptive multitasking, it would take too long, and we'd corrupt our packets essentially because the buffer would underflow. So that's essentially why we moved from the V1 board on the top to the V2 board on the bottom. And in that case, we're using a microcontroller, essentially as a large buffer. So the Pi feeds the microcontroller with the data we want, and the microcontroller, which runs in real time, will keep the transmitter fed as needed. So that essentially eliminated the problem immediately. It's a bit more complicated and it's a bit larger, but it works great, and it's what we needed to do. So that's what we did. Um, and then I guess I'll talk about thermals a little bit. So the transmitter itself, the rectangle there, it idles around 60 degrees on the ground. Um, and once it sort of started rising, it started to cool down until it got to about -5 degrees. And then as it continued to rise, the temperature actually started to go up. And the reason for this is air will cool down rapidly as you rise, but eventually it'll start to thin out. So you get a cooling effect at the beginning, and then it'll start to thin, and you sort of lose that thermal transfer, and it'll start to heat up again. Interestingly, even at 27 kilometers of altitude, it was still running a little cooler than it was on the ground. It was at about 40 degrees instead of 60 degrees. So yeah, I know I was thinking a lot about what the sort of final temperature would be, if it would be a lot cooler than it was at the ground, or it would be a lot hotter. And it's interesting to know that it is slightly cooler, but it's not super far off. Um, Oh, and I should mention we did launch it with a small heat sink on that rectangle, so it did get a bit more thermal transfer than you might expect from the image. But yeah, the heat sink did help a little bit. So yeah, I'll talk about the ground station a bit. So the image on the left is the ground station we used last Saturday. So I've got an Arrow antenna on a tripod. The Arrow antenna is pretty popular for satellite work. That's why I originally bought it, but it's also super useful here because there's a 2-meter section which we're using for APRS, and that is sort of running into a Kenwood TM231A radio, and then we're decoding the APRS packets in the laptop. So we didn't strictly need to do this. It was just something nice to have instead of relying on the APRS IS network, just in case that happened to go down when we needed it. We were receiving the packets ourselves. And then the 70 centimeter portion of the antenna is connected to an SDR. It's kind of hard to see, but the SDR is mounted onto the tripod itself. That's just to shorten the cable run for RF, just to keep our signal as strong as possible. And we're feeding it from the SDR directly into the laptop just over USB. I brought a low noise amplifier, or LNA, with me to the launch, but the signal was so strong that I never ended up using it, and we just kept it in the box. So yeah, I'm curious to see how it would do at a higher range where the LNA was actually necessary, but for this launch, the signal was so strong, we didn't even have to really point the antenna especially accurately, and it was still working fine. So we're definitely exceeding sort of the necessary signal requirements. And then on the right side there is the software itself. So this is a slightly older version of the software from a previous launch. This was before we added video, but it looks largely the same. So on the left side is the latest received image, and then on the right side there's a couple of graphs which are essentially for debugging and seeing how, or I guess evaluating how good our signal is. And then below that is the text telemetry. And like I said, this is an older version of the software, but the current version looks identical, except it has a video as well as imaging. So yeah, there's pretty much not much new to show there. Yeah, so these are just a few pictures from the day of the launch. There's the recovery in the tree there, and a picture of the payload, and a picture of the lifting train. And I figured I would just open it up to questions.
Stephen, when you're pointing at the sun, do you have some kind of a filter that is on the camera that allows for an easy view of the sun?
Yep. Yeah, so David can probably speak to this more. I think I saw him on the call. We have a filter which I believe reduces the output of the sun by something like 10 to the 5. And that's sort of on a servo motor, so we put it in front of the camera at the launch time, and then when the eclipse actually happens, we sort of take that filter out of the optical train, and then we can see the actual image.
Yes, it's a Batter filter from an astronomy group in Germany. So it's a very thin filter, which, because it's so thin, doesn't cause any optical distortions to the image. And it has an optical density of 5, which reduces the light intensity by 5 powers of 10. And the net light intensity, by having that optical density of 10, brings the intensity of the sun roughly down to the intensity of the moon. So during, of course, during the partial phase, the filter is on, and then we have to carefully move or go to have the filter in place. Ken Strauss designs a mechanism to move the filter in and out. And so during the totality the sun is completely blocked out, and the light source we have is the sun's corona. And the sun's corona happens to be approximately the same intensity as the moon's intensity. So that's the basic situation.
Thank you.
Stephen, I have a question. The LDPC coding and decoding, are those libraries that you found publicly available?
Yeah, so those are actually used from the VE9 project. I basically reuse that. There are some libraries I looked at, but they sort of have everything set up perfectly for a 256 byte packet before the encoding, which is perfect for us. So I ended up just reusing that from their project.
Thank you. And the image that was in the last image showed the payload in a tree.
Yep.
Was that what was recovered?
Yep.
Wow. Okay. It didn't look that damaged.
It survived remarkably well. Only very minor damage. Tom Sisk built the payload. It has to be light as weight as possible, but yet strong. It also has to be able to float, because if it lands in a lake, we have to retrieve it from water. But the only thing that was lost from the payload, we had two commercial safari cameras, sort of fake GoPro cameras, one at the top and one at the bottom. The bottom one was lost during the retrieval process. It took the retrieval team 7.5 hours going around the countryside in New Brunswick to get it. And it was J.D. Irving cooperated fully. It landed on their property. We were in full concordance with working with them. And it was harrowing getting it. We used a 3/4 ton truck, not a half ton, to go into this stuff. We had to go through these logging woods of J.D. Irving's, which had fallen trees on them. So we proceeded, or not me, but the 4-member team had a chainsaw, and they cut these trees blocking the road periodically, and got to the location, which was determined by spot trace device, GPS spot trace device. And it was dense wood area, and it was very easy to get lost. We had a beeping mechanism on the payload. So you're walking around in this dense wood, and you hear this beep, and then you're thinking, oh, it's going to be on the ground. But no, you got to look up. Look up. There's the beep up there. So then when they got to the payload, they just shook the trees somehow, and the payload came down with very little damage.
Are there other questions?
Yeah, I've got a question. As some of you may or may not know, I have a license to fly hot air balloons, so that I'm familiar with stuff that goes up and comes down. What lifting gas did you use? Hydrogen, helium, and what was the size and composition of the envelope itself?
It was a 2,000-gram K-Mont balloon, latex balloon. I can't remember the exact number of how many liters of helium we put in. We're using helium, not hydrogen. The helium is, by my standards, very expensive, but this is a public endeavor. And so it would be much cheaper to use hydrogen. Hydrogen is used almost exclusively for instance, U.S. Weather Service and Canadian Weather Service, but nobody feels, I guess, comfortable using hydrogen. Does that answer your question?
That does answer my question. You don't happen to know right offhand, you're a metric kind of guy, but what the volume of the envelope was?
Well, I should have these numbers on the tip of my tongue, but by the time it gets up to its maximum height, the diameter of the balloon is in excess of 10 meters.
Okay, that's good enough. Thank you.
David, can you remember on the previous flight, like we had 275 cubic feet?
We used 1 1/4 or maybe 1 1/3 helium tanks, and each one containing about 290 cubic feet. Does that sound right, Tom?
Yeah, I think that would put it just about exactly.
Right. And the legal limit is if you are at 115 cubic feet or above, you have to go through all this regulatory process, which took us more than 6 months to get through. And in addition, we have to have $5 million of liability insurance. And a company was formed, a numbered company, to make this operation go forward.
How many people altogether would have been involved in this project?
On the engineering team, but it's of the order of 10. It's not 10, but we have students. We've had 8 students in total so far working on the project, 4 1 year and 4 last year. There are 6 or 7 engineering science people on the team, from Dr. Don Pluis he now lives in Victoria. He is the science math guy behind this. And Ken Strauss is an engineer in Coburg. It's excellent engineer of machining, doing this incredible work with the Agile Eye. And Tom Sisk, of course, is in Fredericton, doing all this very good stuff. And of course, there's Stephen. There is Lewis Cobb. And we have, in addition to the engineering, we have support staff. We have whole teams to run this operation. It's quite complex, and a person called Chris Doherty, who knows how to deal with things like this, but he is what I would call the project manager. And so we have like a security team, a recovery team, the science electronics team, and so forth. So he's running that. And my brother Lawson Hunter is heavily involved in financing this and getting corporate involvement and community involvement to move forward. My brother Gordon Hunter, who lives in Florenceville, his son Sandy Hunter has a company called Cazador, and he is doing videos and documentation of the project.
Quite a few people involved altogether.
Sorry if I've left anybody out. There are also the Hunter brothers in the Hunter Brothers farm here in Florenceville who have been assisting, and so forth.
Thank you for pasting the link, Stephen, to the random channel in the Slack group of the Fredericton Amateur Radio Club to alert us about this. What was the amateur, well, anyone there, what was the amateur radio call sign of the APRS beacon?
It was a VE9QLE-11.
Oh, and I would like to say, Brent, there's another Brent in your group. Sorry, what's his last name?
Brent Taylor, VY2HF.
Yeah, so Brent Taylor, I want to give him credit, especially last year, because I'm not an amateur radio person, and so I approached your group, and Brent helped us last year with the first APRS, and it was under his call sign that the first flight went forth. It actually got off the ground. We had a test flight in April of this year. We didn't have enough helium, and we could have, anyway, we didn't lift off. And then in June 17th, we had a successful liftoff. And during that flight, his APR system was lost. And so now it's Stevens, with Stevens call sign.
Thank you. Are there any other questions? All right. Well, thank you very much, Stephen and David, and the rest of your team, Tom, and I guess I think one of your team members might have left. Oh, and Ken. There's a fantastic amount of technical work that you've summarized very briefly here, so thank you very much.